Hi, my name is Adriano Fabro. I'm from the University of Brasilia, and this work is an ongoing collaboration with Dr. Han Meng and Dr. Dimitrios Chronopoulos from the University of Nottingham in the UK. And it's about manufacturing variability of 3D printed broadband multi-frequency metastructure. Okay, so this is an overview of the presentation. I'll give you some scope and motivation, and what is a multi-frequency metamaterial. I'll talk about a little bit of metamaterial variability from 3D printing, and I'll introduce the concept of phase and attenuation change, some numerical results, and concluding remarks. Okay, so we are interested here in metamaterials for vibration attenuation in the sense that they provide vibration isolation at the transmission path. So you introduce it between a source and a vibration source or a noise source and a receiver, okay? And then it creates a sort of mechanical filter, which we call the band gap, okay? So we know that additive manufacturing has allowed for various metamaterials designs, okay? But as any other manufacturing process, it introduces variability, and resonator mistune has been shown to affect the band gap performance in several ways, okay? So you can have more details on this reference here, but typically we look at the transfer receptance between an excitation and response points, okay? And we look at these band gaps here, which provide us some sort of vibration attenuation here. So the question is, how does a metastructure with mistuned resonator performs in terms of band gap widening and maximal attenuation, specifically for our case analyzed here, okay? So which is, we are looking at what they call a multi-frequency metamaterial, which is basically a metamaterial design with what they call non-symmetric resonators, okay? In here, we are using an analytical model in terms of transfer metrics, assuming all abelianly being theory for the host structure, cantilever resonators with lumped mass at the tip with no rotation inertia. These insertions here are modeled as added masses with rotation inertia, and more details can be found in these references here, but with the highlight here is that the resonators, or the two resonators configuration, is such that they act independently and they create two band gaps, thus increasing the total attenuation, okay? So here is how we can manufacture that, or how we had manufactured this kind of structure using this technique, which is the powder bed fusion process. This is just some of the material constants and the geometrical constants that we used or designed for metamaterials. So just to highlight that we had the 17 segments or 17 what they call unit cells on this metamaterial, okay? We also know that metamaterial can have some sort of spatial correlation, which can be really important, okay? So in this work here, it's shown that we can measure that. We actually can quantify this spatial correlation, and there's also an additional correlation between some of the material properties, which indicates that there is underlying process or underlying parameter controlling both at the same time, okay? Okay, so here in our case, we used a more simple approach to characterize this variability, thinking that different printers or different processes present different variability. And then we can quantify that, and we can use this spatial correlation assumed from a model that we developed on that previous publication, okay? So from here, we have some correlation on the properties, on the material properties. And here is some of the typical mean values and standard deviations and coefficients of variations found by our printer at the University of Nottingham. Okay, so here in this we have the periodic design of the metastructure, which is typical for metastructures, and then the numerical response of this periodic design, in which you can see two band gaps here, which is two dips on the transfer receptance. Okay, so this provides some sort of vibration isolation, and is explained by the wave number, or in here the normalized wave number. So the black bits here are the real part of the wave number, which indicates the propagating waves. Okay, and the red bit here is the imaginary part of the wave number, which indicates the non-propagating wave. So this is telling me that in this region I'll have a band gap, in this region I'll have a band gap as well along the frequency. So in periodic structures, it's well known that we can use the Bloch theorem to calculate these wave numbers. Okay, I'm not gonna get into details, but basically using this transfer matrix, you can write it or rewrite it in terms of a eigen problem and extract these wave numbers. Okay. For nearly periodic structures, I can't do that directly, but we can define a certain equivalent wave number for a finite length structure, or for a finite number of unit cells. Okay, so this wave number we can extract from an equivalent eigen problem here by multiplying the number of transfer matrices, or the suitable number of transfer matrices here. And from that, we can get something which we could call equivalent wave number with a real part and imaginary part. And the real parts, we call this total phase change, and the imaginary part, the total attenuation change, with similar interpretation from the wave number diagram that we have for the periodic structure. Okay. Here we have an example of nearly periodic structures based on that metamaterial design. So we have different profiles here for the tip masses of the resonators of the non-symmetric configuration. Okay, so the blue is the periodic, and the red, it's two profiles providing larger band gaps, and then the equivalent interpretation in terms of real and imaginary parts of wave number. So one question we can ask ourselves here is how or do the randomness in the resonators affect attenuation performance? We know that they do, but how do they do that for this multi-frequency design using our printer or a different characteristics of printer? So we're trying to investigate that on this work here. Okay. For that, we have to impose some sort of spatial correlation and mistune this the resonators by some sort of random disorder modeled by random fields. Okay. Typically, we want to model the spatial correlated uncertainty with that. And in here, we assume that for this numerical investigation, that only the tip masses are spatially distributed, described by this equation here, in which this constant here is my mean value, and this is my statistical dispersion, and this is like my spatially correlated random variables. It's a vector with random variables. We assume the Gaussian homogeneous random field, but with this correlation function, which is the same that we identified from that previous work. Okay, so just to highlight that for increasing correlation length, we have a smoother variability, or smoother spatial variability. Okay. So here we are looking at the response assuming correlated disorder generated by a single sample of my random field with this correlation length here. And we are increasing the dispersion parameter of the variability of the tip masses here. Okay, so in here we are assuming that the values of the tip masses are the same. So we have different natural frequencies by changing the size of the cantilever beam on the resonators only. And then you can see that by increasing my dispersion, I do affect my band gap widening or the length, this frequency region here, but also decrease the total attenuation, but still with not too bad values here. Okay, so an equivalent interpretation can be found by my normalized wave attenuation, or my equivalent wave number here, looking just at the imaginary part, which is the bit that gives me the information about attenuation only. Okay, so summarizing, by imposing this spatial correlation and increasing the dispersion parameter, I can actually improve my total attenuation of my when compared to my periodic design. And here we can look at the same analysis, but looking at the total displacement field. So this axis here is the position along the beam. This is the frequency, and the colors indicate the vibration amplitude, with reds indicating the lowest possible values here. Okay, so you can see that from this almost periodic design with very low variability, we have two straight lines here indicating my band gap regions. And as I increase this value, I tend to modify not only the length of these band gap regions, but also how they behave along the metamaterial, which causes what they call wave trapping and several other phenomena there. So more details you can find on this reference here. Okay, but now we want to further explore this previous result by keeping a relatively small variability in terms of disordering, but changing the correlation length. So we are looking at how this correlation length affects my response, and we can see here that by decreasing the correlation length, I actually have the same or similar results as by increasing my dispersion parameter. Okay, so I tend to have a slight increase on the band gap widening. Okay, and a decrease on the total band gap attenuation, and we can see that here on this result as well. Now we also can look at this effect on the displacement field of my band gap. So by decreasing my correlation length, I can see a similar effect of wave trapping here. Okay, so bear in mind that this is these results are based on a single sample of my random field. I can actually optimize by choosing different random samples. I can get improved results in terms of vibration attenuation or in terms of band gap widening. Okay, so just to conclude, we showed some investigation of uncertainties in terms of attenuation performance of metamaterial, and I want to highlight that the spatial correlation plays an important role on the attenuation performance. And we can also use random field proposed on previous works. Okay, so my experimental data also show correlations between Young's modulus and mass density, and by actually using that on the numerical results, I can further increase the effects of attenuation performance, although it's not shown here. We also seeing that shorter correlation lengths can induce wider band gap, or they tend to induce wider band gaps, but with smaller attenuation performance. Okay, this is because of internal reflections and wave trapping, and the overall effect can be investigated by using this introduced concept of total phase and attenuation change. Okay, also distinct samples of with the same statistical features can produce very distinct band gap performance. This comes to the importance that robust design is very important for ensemble statistics. This is actually work in progress and also individual structures can be tuned for specific applications by specifically tune certain samples of my random field when producing these types of metamaterial. Okay, so I just want to thank you for your attention.